In this video lecture, we will concern ourselves with the issue of determining how long ago a once living thing, could be a plant, could be an animal, could be a person, how many years ago that living thing stopped breathing and eating, stopped taking in carbon, for example. Well, I'll remind you that various isotopes, which are radioactive, have a property called its decay constant, lambda. We'll see how lambda fits into the scheme of things soon. Let uppercase T represent the half-life of the isotope, the number of minutes, days, months, years, whatever it takes for half of a radioactive sample to disappear, to have decayed. I showed you last time a graph and an equation. It's the exponential decay equation. You see once again the appearance of the decay constant lambda. In order to determine the relationship between the decay constant and the half-life, we use the fact that when lowercase t, the number of years or months or weeks or days that have gone by since you first looked at your radioactive sample and counted how much was there, let t be that number of years, months, days, or weeks. Well, in a period of time known as the half-life, half of what you used to have is now gone. So if you used to have at time t equal to 0 a quantity of mass m naught, then a half-life later, capital T later, you'll have remaining only half of what you started with, 1/2 of m naught. Divide out the m naughts, and this is the equation you arrive at. Take the natural log of both sides. Recall that the natural logarithm operator is the inverse of the exponential operator. And so what's left on the right side is negative lambda t. And this is negative 0.693. The negative signs on each side of the equation cancel. Solve for lambda, and you have this important equation. If you know the half-life of some radioactive isotope, and it's constant, whatever it is, forever, then you can calculate the decay constant. Give me the half-life, and I'll tell you the decay constant. Well, we'll look at a very simple example. Uranium-238 is radioactive. Its half-life is 4.5 billion years. Suppose we have 20 nanograms of that isotope right now. We ask the question, how long will we have to wait until the amount of isotope we have left is only 12 nanograms? Start with 20. How long do you wait until there's only 12 left? Well, the first step is to calculate lambda, the decay constant, using the equation I showed here. 0.693 divided by the half-life, this is what I got. Notice the units are reciprocal years. Now, we use the decay equation here, substituting for the masses, 12 and 20, and there's the rest of the exponential power. Divide both sides by 20, and this is what you have. Then the final step would be to take the natural log of both sides. The exponential disappears. Simple equation you get to solve for t. This is what I get. Alternatively, you could use the solver feature of your calculator to find the unknown time t. Well, let's put that example away. And let's talk about how one could use the information that we know well about carbon-14 and how it decays and how rapidly it decays and what its half-life is, to learn how we can determine how long ago an organism, once alive, then expired. When it expires, no longer is it breathing or eating and no longer taking in carbon, which will replace the carbon-14 that this once living organism will be losing for X number of years. let's look at this situation. First, we calculate using the known half-life of carbon-14, 5,730 years, to calculate the decay constant for carbon-14. Let n naught, or n subscript 0, be the number of carbon-14 atoms per gram in living matter of a certain type. Maybe it's the bone of an animal of a certain kind, or other tissue of a certain type in this living organism. 0 subscript means that this is the number of atoms per gram of material that exist when this object has been dead for 0 years. In other words, it was alive, now it's dead, now let's wait and see what we have later. N, without a subscript, represents the number of atoms per gram in a deceased animal or a deceased living organism, perhaps a plant. We have the decay rate equation shown here. Instead of m's for the masses, I'll let n be the numbers of atoms present for n naught in a gram of living tissue. Once that organism dies, the number of atoms per gram in the dead specimen or artifact or fossil is less. It symbolizes n. So if we know how many atoms of carbon-14 there are per gram in a live specimen, and measure how much there is now, and knowing the decay constant, we can solve this equation for t, which would be the number of years that have gone by since that animal stopped having its carbon-14 refreshed by eating things from the biosphere or breathing things, breathing air. And so you know 1, 2, 3 of these 4 quantities in this equation, the fourth being t, the number of years that have gone by since that animal died. And so we will know how long ago that animal or that plant was living. And thus we have a way of dating old things that are dug out of the ground. We discuss the use of this dating procedure applied to determining the date or the age of the flax plants that were used to weave the famed Shroud of Turin. You can read about that in the chapter relating to this topic.